Okay, welcome to the second video and part 3 of the series of lectures on quantum computing. So in this video, we're going to look at the first half of part 3, in which we're going to look at NMR quantum computing and quantum computing with optical systems. So we'll jump right in and start with NMR. So what's the motivation? So I sort of want to sell you a little bit on each of these quantum computers. So at the start of introducing each one, I just want to convince you on why you'd want to use it. And I think there's sort of two clear reasons why someone would want to use NMR. One is that the spectrometers are already built. So what you're looking at to the right there, I'll explain the details of the spectrometer in a moment, but this is the spectrometer. So NMR, nuclear magnetic resonance, is a phenomenon that's been well studied since the 50s. And so when it came time to use it as a quantum computer in the 90s, a lot of its techniques had already been well refined. So the spectrometer, you don't have to build your quantum computer, you pick up the phone, make an order, get your spectrometer, take it out of the box, plug it in, and get to work with a few more steps, maybe in between in the plugging it in. But it's already pre-made. And another reason why people currently would use it, besides it being sort of easy out of the box, is that if you're doing something with a few qubits, you really can satisfy all the Vincenzo criteria very well. So you get excellent control of a few qubits. Should also mention, though, that you can measure them well, single qubit gates, 2-qubit gates, initializing the state. So there's a caveat with initialization, but all these things are possible and have been done many times with just a few qubits. Historically, because the NMR techniques have been well honed from the 50s to the late 90s, so I think I said 92, but I should have said 97 was when it was first used, it was allowed to be one of the very first quantum computers that people were able to implement quantum algorithms on. I mean, it was the first one. And so it's historically quite significant. And since that first algorithm, many other quantum protocols have been first done on NMR. One very notable one is quantum error correction. So I mean, same with classical computers, you need a way to correct errors. Quantum error correction is a whole topic in and of itself, but the idea is that we need to have some type of way to correct errors even on a quantum system, and quantum systems have their own challenges to correcting errors. But anyways, that's quantum error correction, and it was first done with NMR systems. So the way I'm going to approach it now, hopefully you're somewhat sold on NMR and get where it fits in the big picture. I'm going to go through each of the DiVincenzo criteria. Well, most of them. My goal is for you to have a good understanding of the physics of these systems and to have a sense of their strengths and weaknesses. Sort of more of an engineering level picture of how these things work, and a physics level picture, and maybe a little bit less mathematical detail, just because, this topic of reviewing these 4 quantum computers, that's a whole graduate level course that's offered at Waterloo. And so I'm trying to summarize, give you a broad picture of that entire course in a couple lectures. Okay, enough caveats and disclaimers and the sorts. So qubits. So the qubits are encoded in the magnetic moment of certain nuclei in molecules. So you're familiar with the concept of spin in this course. And one thing you may already know about spin is that intrinsic angular momentum produces a magnetic moment for the nuclei. So here I have 2 molecules that are used in NMR experiments. One is chloroform, which is a 2-qubit sample, and the other one's trichloroethylene, which is a 3-qubit sample. So this entire molecule here is your quantum processor. And the spin half qubits, or the spin half nuclei, will be your qubits. And not just any spin half nuclei, it has to be ones that the spectrometer, their frequency, the spectrometer can measure. So here, for instance, I have carbon and hydrogen, and I had the frequency in which they precess in the spectrometer. This will depend on the magnet in the spectrometer. So I think this is for about a 12 Tesla magnet, but what's important is to see that they precess at different frequencies. And you'll see in a moment why they precess and how they precess. But the idea is that these nuclei in the spectrometer will be twirling around with different frequencies. And certain frequencies can be measured by the spectrometer. So the spectrometer that I have in mind here when I call this a 2-qubit and this a 3-qubit sample is one that can measure carbon and hydrogen. So they're different frequencies, I can measure them separately. In this 3-qubit sample, I actually have 2 carbons and a hydrogen, and I needed some kind of way to measure them each independently. And so these 2 carbons need to have different frequencies in which they're processing. In practice, they will, and that's mainly just because their environment is different. So these other nuclei they're coupled to create different electronic environments, which will influence their frequency. But the gist of this slide is that the molecule is your processor, and the nuclei are your qubits. So when we actually go to create an NMR sample, I don't take a single molecule and drop it into the machine. What you do is you get a tube about the size of a long pencil, maybe a little bit, well, you can see it there. It's a little bit thinner, but about a pencil. You fill it with some solution, and you put in many, many copies of the molecule in. One reason that you need to use many, many copies of this molecule is because the signal produced from a single molecule is much too weak to be measured by a spectrometer. So we need, 10 to the 23 some odd identical copies of the molecule. So you can think about these in 2 equivalent ways. And I think this is really where students get stuck conceptually with NMR, is interpreting this result. You can either think of the molecule as, well, you can think of each molecule as a quantum processor, and your tube consists of 10 to the 23 different quantum processors, and you act on all of them and you measure all of them. Or you can sort of just imagine your sample, your entire sample, as one processor in which when you're taking measurements, you're going to be limited. Maybe you don't see it as a limitation, but you're going to be limited to taking ensemble measurements. So you measure the entire probability distribution and not a projective measurement. So, I mean, if this is conceptually challenging for you, I mean, you can't ask me questions live. You can email me after, but maybe just pause and like sort of sit and think about this to make sure this part is clear of what's your quantum processor, what's your qubit. If that's clear, let's see what it looks like. So if you walk into an NMR lab, you're going to see 3 distinct components. You're going to see a classical computer that's used for controlling the spectrometer. You'll have this box here that takes care of all the electronics. And then this here is where the magic happens. So let's open up and see what they look like on the inside. So this is just the same sort of picture, but schematically, you have your classical computer. So this is where you'd sit and control the spectrometer. You have your NMR console, which takes care of all the electronics. And then here's the, like I said, where the magic happens. So this is your sample. This is the pencil I showed you in the last picture. And there would maybe be a staircase, and you'd walk up and you'd drop the sample into this probe here. What's surrounding the sample is an incredibly powerful superconducting magnet. And we'll see what that magnet does in a moment. But it creates, well, okay, we'll see the effect it has on the sample in a moment. But what it does is create a very strong magnetic field along the axis of the spectrometer. So if we call this direction up and forth, I'm like 90% sure you can see my mouse. If you can't, this won't make a lot of sense. But if you follow my mouse, this direction is the z-axis, and it creates a magnetic field along that axis. So you drop the sample in. And really, right here is where all the interesting physics is. This components around it are just so that you can make this interaction happen and you can control this interaction. So it's a superconducting magnet, so it needs to be cooled. So around it, we have liquid helium and liquid nitrogen. We have both because liquid helium is very expensive. So the nitrogen helps insulate the helium. And these are like the ports to fill that up. But all the other stuff is just to keep the magnet cool. And all the stuff over here is to be able to control the electronics that will be used for controlling the NMR sample. So that's the spectrometer. And so we have our qubits, they're in the spectrometer. Well, what are their states? So if I just hold a sample in my hand, I'm just sitting in my room holding a sample. There's no magnetic, well, there's barely any magnetic field here in my room. So the nuclei, and here I'm just drawing them as the nuclei of interest. So I really should have a whole molecule. That gets messy. So just imagine that these molecules are somehow single nuclei molecules that I'm using in a spectrometer. Let's just pretend. So I have all these different molecules, and their magnetic moment is oriented in all these different directions. For those not familiar with magnetic moment, you can just think of it as a very tiny bar magnet. So I have tiny bar magnets floating around in the solution, and the tiny bar magnets are pointing in any direction. So if I look at the total magnetic moment from adding up all these little bar magnets, there's no net magnetic moment in the sample. So that's what this mu is, it's 0. So if I go to my block sphere picture, I have nothing. There's no qubit there. What happens though is I drop this sample into the spectrometer, and now there's this overall really strong magnetic field. And so the magnets, they're not going to all necessarily align with it, but there's going to be a slight energy preference to being aligned with it. So it looks like here, like one of the nuclei just disappeared. This is just my way of showing that of the many, many, many nuclei, now they're mostly, on average, they're aligned with the magnetic field of the spectrometer. So you have this magnetic moment pointing along the z-axis. So now you have your qubit. And so the state of the qubit on the block sphere is this magnetic moment. Or at least that's a way to think about it, or a way to understand it. I want to be careful to say it is this, because we're talking about lots of different things. In one moment, we're talking about something more abstract, like a qubit state. And then in other moments, we're talking about magnetic moments and many, many nuclei. So that's why I say thought of. It's not because it's imprecise. It's just that we're moving back and forth between the conceptual and the physical a little bit. So you have your qubit state given by the magnetic moment pointing along the z-axis. So now another effect that happens, which is of interest, I remember before I said the nuclei are precessing. It didn't seem like it from what I've said so far. Well, if you take a bar magnet, so let's say my pencil's that bar magnet, and I align it with a stronger magnetic field, what's going to happen is that it experiences a torque. So this is like, second year E&M, and it's going to cause it to precess. If it's off to the side a little bit, it's going to cause it to precess around the z-axis. If it's off like perpendicular, it's going to precess even more intensely. So the nuclei are precessing. And that's what their precession frequency is. It's the frequency of the precession, and it depends on the properties of the nuclei, and it depends on the chemical environment of the nuclei. And it depends on the strength of the magnetic field. So a few different factors there. So we have our nuclei, they're precessing in our sample, and we now want to control them. And so we need two things. We need 1 qubit gates, and we need 2 qubit gates. So how do we do 1 qubit gates? Well, remember that when our magnet, we just said, when it's in that magnetic field, it's precessing around the axis of the applied field. What we can do is use that same property to create rotations around the block sphere. So you take a radio frequency pulse, that's just the correct frequency of the field, and you apply it along the axis in which you want the qubit state to rotate. So say I start originally along in the 0 state, and I want to rotate to the plus state. Well, I apply a magnetic field along, going from the negative y-axis to the y-axis, and I have to apply it for the right intensity and the right amount of time in which the qubit state rotates. Once it gets to this point, I stop the RF pulse. And so as long as I can do this along any 2 axes, I can do any rotation from one point on the sphere to another, and you can apply the pulses anywhere in the XY plane. So we're good. Those of you who maybe are really getting it will have a question of, well, the nuclei are precessing, so how do we apply the RF field from one axis? It's a great question. What you have to do actually is apply the pulse precessing with the nuclei. That way, from the nuclei's perspective, it's always from a fixed axis. But for me sitting in the lab, it looks like the field is being applied at different points. It's just going with the frequency of it. So those are 1-qubit gates. And now we have this way of controlling them, but we need some kind of way of coupling the qubits together. So what do we do? Well, nuclei interact already with each other with something called the J coupling. And in short, the nuclei interact with the electrons around them. The electrons are shared between different nuclei. So these electrons mediate some type of communication, some interaction between these different nuclei. And so the evolution of one nuclei will depend on the state of the other nuclei. So there's different ways you can regulate this effect to create 2-qubit gates. And essentially, they all work in the same way. You apply some pulses, you wait, you let the system interact, and you apply some other pulses. So you're essentially mediating this natural interaction to get the effect that you want. So what this picture shows here is 2 nuclei, and I'm putting them on the same block sphere for contrast. So you have 2 different nuclei, one's blue, one's red, and I apply some pulse, I rotate them into the x-axis, and the pulses are quick. They happen on the order of 10 to the -6 seconds. And now they're here, and the difference between the 2 nuclei is that their neighbor is in a different state. So the blue one, their neighbor's in the 0 state, the red one, their neighbor's in the 1 state. Because their neighbor's in a different state, and they have a coupling with that neighbor, it's going to change their evolution. So one of them is going to evolve along this, in this way, the other one's going to evolve that way. So what these are just like leftovers from me using this figure elsewhere. But this is me saying it's a y rotation. So I'm applying a pulse along the y-axis, and pi by 2 is the radians of that rotation. What this u1/2j is, that's just a way in NMR you would denote a free evolution of some time, where the time here is 1/2j, where the j is a function of the coupling. So if the coupling is super weak, I mean, it makes sense, you'd have to wait longer. If it's really strong, you'd wait less time. So if being proportional, waiting 1/j is reasonable. So you wait for it to evolve, and then you apply a couple more pulses, and now it's in this state. So what I've done here is a conditional gate. So blue stayed in blue, but red underwent a bit flip because its neighbor was in a different state. And if you'll remember from John's lecture, that's how a control NOT gate works. So we have control NOT gates, we have single qubit gates, we have universal control. So measurement then. Well, this is also some like basic E&M physics for how this is done. So the nuclei are processing, and when they're processing, they have a magnetic moment, so they have a magnetic field. And as they're processing, they have a changing magnetic field. A changing magnetic field induces a current. So what we do is we put coils around the sample, tuned to the frequency of the different nuclei, to measure their final state. And so, and like we said before, this is why we need ensemble measurements. These coils can't detect the magnetic field produced, the current produced from the changing magnetic field of a single molecule. So you need many, many molecules to get a detectable signal. So these coils are sort of wrapped around the sample. When it gets dropped into the spectrometer, the coils are already there. So these coils pick up the current. And so that's the foundations, I guess you could say, of an NMR experiment. There's one point which I didn't go over, and that's sort of how to initialize the system. It's a little bit more complex, but the essential idea of it is that you prepare something called a pseudo-pure state. So instead of getting all the nuclei in your sample to all be in the 0 state, you get most of them to be in the 0 state, and the ones that aren't, that's sort of the rest of them, on average, are equally distributed. So that's part of the sample. You can sort of think of it as sort of just hanging out on the side, not doing anything. That's a very loose way of thinking about it. because it's not like in the sample you actually have a few that stays in the zero state and the rest of them are random, like they're interchanging back and forth. So it's somewhat nuanced, but that's maybe one of the more advanced topics in how NMR quantum computing works. But just to see the 5 criteria, so we want a scalable, well-characterized qubit. Well, our qubits are the nuclear spin within a molecule, and we distinguish them with their different precession frequencies, which are also known as Larmor frequencies. So if you come across either of those terms. Scalability, well, that's going to be limited by the molecules in our sample. So if you recall, the number of qubits we had depended on our molecule. So maybe I could find a molecule out there that's, you know, 100, has 100 spin-off nuclei, and they all have very distinct frequencies. That would be great, but we're limited by what nature gives us. And so the largest molecule that's been used for NMR quantum computing that I know of consists of 12 qubits being controlled well. The other issue, just as you add, as you get to larger molecules and you, sorry, not larger molecules, as you go to try apply more pulses, your signal to noise ratio is also going to be another limiting factor. So I mean, you could do 1,000 qubit gates, and so, you know, you're somewhat limited in which quantum algorithms can be implemented. So I mentioned this sort of pseudo pure state. It's most of the state is in this, most of the samples in the zero state. The rest of it is in this equally mixed state that sort of just chills on the side. Gates, our 1 qubit gates, are done through radio frequency pulses. And so these are called rabbi oscillations. So you have a qubit, you're applying a pulse, and if I just kept applying the pulse forever, the state would just keep cycling around that axis. It would go between 0 to 1, 0 to 1, et cetera, et cetera. Those oscillations are called rabbi oscillations. And the 2 qubit gates come from regulating the J coupling in the system, so between the spins. So you take their natural evolution and you sort of control it to get the 2 qubit evolution you want. Measurements are done as an ensemble by measuring the changing magnetic field in the end. And in terms of decoherence to gate times, decoherence times for most NMR samples, which are used on the order of seconds, while 1 qubit gates take 10 to the -6 seconds or microseconds, and the 2 qubit gates are in milliseconds. So the 2 qubit gates are really the limiting factor here in terms of, well, and the decoherence time, I guess, but between the 2 different gates, it's the 2 qubit gates that take 1,000 times longer than the 1 qubit gates. So those are the main issues. Okay, so we're going to move to our second implementation, and that's linear optical quantum computing. But first, let me sell you on optics. So let's say you're an NMR experimentalist, and I'm trying to bring you over to the optical side. Well, one argument I could make is that the tools used in linear optical computing are much more accessible and cost efficient. So things like phase shifters, beam splitters, single photon sources might be more expensive. I mean, single photon detectors might be a little bit more expensive. I mean, they're definitely more expensive than polarizers and beam splitters. But overall, it's still going to cost you less than buying a spectrometer. So it's easier to get, and it's more cost efficient. Second thing is that they don't need to be cooled. So we don't have a superconducting magnet, which needs to be brought to crazy low temperatures to work. And really, this is pretty unique to optics. As we'll see with the other implementations, all of them need some kind of cooling that's going to be costly. And then lastly, it's photons interact weakly with their environment. So they don't, since they don't interact, they're not going to bleed as much quantum information to their environment. So the decoherence times are much longer. Historically, optics was actually one of the first systems that was thought of for quantum computing. I mean, effects like interference are easy to see, and the photons are mobile because they don't interact with their environment, easy to move them around. But as I mentioned before, NMR was used first. So why is that? Well, photons' weak interaction with one another, which is a strength, is also a weakness, because it makes it hard to do photon-photon interactions. And so since photons have this aversion to coupling with one another, it made it hard to do 2-qubit gates. This was a serious roadblock until 2001, where Neil Laflamme and Milburn proposed a way to do optical quantum computing using linear optical elements. So I should mention, the aversion photons had to coupling with one another, there was ways that you could do it using non-linear optical systems. But these are, while theoretically possible, technically challenging to work with. Linear optical elements, on the other hand, are much easier to work with. And linear here means the same thing as it does in, in your math course. It's that the outputs are a linear combination of the inputs. So LOQC, linear optical quantum computing, was born. So there's a few pieces, and if we look at the first DiVincenzo criteria to have our qubits, we need two things. We need to produce single photons, and then we have to encode the qubit in the single photons. Getting the single photons, though, is not so easy. So why is that? Well, let's imagine our ideal single photon source, our dream single photon source. Well, it would be able to produce single photons, first of all. It's not going to produce two or more. It's going to produce the photons the moment we need it. So we press a button, we get the photon. We don't press a button, and we might get it then, we might get it in a minute, we might get it in an hour. That'd be pretty annoying. So we want it the moment we want it. The photons are going to be moving in the direction we want with the frequency we want. So pretty much, it's not like a random photon we're getting. We're getting a photon with the properties we want, so we can engineer the rest of the system accordingly. And we want it to be somewhat replicable. So we have multiple sources. We want all the photons from those multiple sources to be identical. So there's a few ways to do it. I'm going to look at 3 of them here. I mean, these are just 3 that are somewhat illustrative. There are many others, and it's an active field. So if something came out in the last year that's, incredible and way better and revolutionary, I don't know, and it could be possible. Actually, speaking of which, Professor Reimer is sort of like an expert in this area. I shouldn't say sort of, he's an expert in this area. So he would know if there's been some new development. So spontaneous emission is the first one we're going to look at. So you have some atom. It's a 2-level system. Well, we'll look at 2 of its levels. Atoms have many levels, but we'll look at 2 of them. And I shine some source of photons in on it. And it doesn't have to be a single photon. It could be like coherent light, so a bunch of different frequencies. I just sort of blast it with light and one of those photons will have the right frequency that the atom will absorb it, and it goes to its higher energy level. And it enters a metastable state. So what's metastable? It's sort of like having a soccer ball in your head. You can like hold it there for a moment, but eventually it's going to fall off. So it's stable, but not for long, and a little nudge, it's going to come off. So the atom gets excited to this metastable state, and eventually it falls off. And as it goes down to that lower energy level, it emits a photon. And so that photon is going to have a frequency that matches the energy gap. So then we get a photon of the frequency we want. But the problem is that we need an isolated quantum system to do this, which isn't easy. And the photon's emitted in a random direction. Now there's techniques to mitigate that, like with NV centers or quantum dots. But in general, it's going to be emitted randomly. Another option is weak coherent light. This is sort of the most, I think, rudimentary, I guess, or elementary approach to it, where you just have a really, really weak light source. So coherent light is how you classically have interacted with light. It's not single photons, it's just a bunch of different photons, maybe different frequencies, different polarizations. So different numbers of photons at different points in space. And so if I have the light be weak enough, then I can argue that if I have any light at all, it's most likely just going to be a single photon. So it's easy, but it's not very consistent. And so it's not reliable enough for quantum computing, but it could be for quantum key distribution, which briefly mentioned in the last video. Another one is heralded single photons. So there's different ways to do this. One is through spontaneous parametric down conversion, or SPDC. Um, Speaking uh, sort of like broadly how SPDC works is that you have this nonlinear crystal. So we do have something nonlinear here to produce our photons. That's okay. It's the linear and linear optical quantum computing is from the actual how you go to implement the algorithms. So we have our some nonlinear crystal, and we pump it with light. And so most of that light is just going to pass through. Some of it's going to be absorbed by the crystal. When it goes to then readmit that photon, it's going to go through sort of like a two-step down conversion. So instead of just dropping and emitting a single photon, it's going to drop 2 levels, and in each of those levels, it emits a photon. What happens then is you have 2 photons coming out always together. So you either have the pump goes right through undetected, or if the crystal absorbs it, you're going to get 2 photons. What's nice about that is you put one detector over here, and whenever this detector goes off and measures that 1 photon that came out, you know that there's another photon over here. So we can get photons with all the properties we've mentioned that we like before, except that since most photons pass through, it's not exactly on-demand photons. It's nice though that if the photon arrives, we know it's arrived. So even though it's like probabilistic, we know when it's going to come, but we can't just necessarily control it. So I'm sure this has been refined over time, and there's like much more maybe elegant ways that this is done now, I would imagine. But this is the general picture of heralded single photons, and the example with spontaneous parametric down conversion. So let's say we can generate our single photons well enough. And I think we are at that stage where there are pretty good single photon sources. We are getting single photons pretty well. How do we encode a qubit into a photon? Well, we're pretty free to pick any degree of freedom we want, as long as we have, so these are called the modes of the photon. So it could be the polarization. We could say horizontal polarization is, so a photon is horizontally polarized is a 0, vertically polarized is a 1. That's one option. But the one that we're going to use here in LOQC is something called the dual rail encoding. So essentially we have 2 paths side by side. So you can imagine them as like 2 fiber optic cables. And if the photon is in this cable, I got a picture for that. If it's in the top cable, it's a 1. If it's in the bottom cable, it's a 0. So the 2 cables together are qubit. So if you want to do a bit flip, you do something you bring the 2 fiber optic cables together and you take them apart, and you have the photon move from one spot to the other. If you want to do a phase, well, we'll see how other gates work, but those are our 2 states. So we have our qubit. We've produced the single photons, we've encoded it. We're going to jump a little bit ahead, and we're going to look at photon detectors. So we're sort of skipping over the algorithm part. That's because detectors are used in creating the circuits in LOQC. So how do we measure our qubits? How do we measure the photons? Well, one thing just right off the bat, with the dual rail encoding, determining if we're in the 0 state or the 1 state is very easy. We put a photon detector on each rail, and then we just see which side the photon was on. But we need certain properties to these photon detectors. One is they need to be sensitive enough. They're going to respond to single photons. That's not very much light. It's easy for them to not detect it at all. On the other extreme, we don't want them to be too sensitive. We get something called dark counts when there's no photon there at all and they still go off. We want them to detect the right frequency. So there's going to be photons in the environment anyways. And our ones that we're using for our quantum computer will be a certain frequency. And we don't want background radiation to cause the detectors to go off. And then lastly, if we're dealing with cases where we have different photons, we have 1 or 2 photons, we're going to be able to distinguish 1 photon from 2 photons. So everything here is pretty doable, except the last one is probably the biggest challenge currently. I mean, as far as I know, and it's an active area of research as well. So what do we mean really when we're saying a photon detector? Well, traditionally, actually first, take a step back. What do we mean by photon detector? Well, we want to convert an optical signal into an electrical signal. So we have light, we want our computer, our quantum computer, we want our electrical system to be able to identify that that optical signal is there. So what we want is to convert optical signals to electrical signals. Traditionally, how has that been done? It's sort of funny to call this traditional because it's Einstein, and Einstein people associate it with like modern. But anyways, the first way to do it is the photoelectric effect. And so what that is you have a metal plate, it's loaded with electrons, you shine light on it. If the light has a frequency such that its energy matches the energy needed for the electron, or yeah, that it needs for the electron to escape the metal. So you can imagine the electron tied with a shackle, and you need a photon of enough energy to break that shackle. Then the electron is freed, and it creates something called a photoelectron. It just means an electron that came from an optical source. And that was actually the reason why Einstein has a Nobel Prize, was because of this effect. So pretty significant. So practically, there's different ways you do it now. I'm just going to mention one here, which is a photo multiplier tube. So in the photoelectric effect, in this picture, I'm sort of shining a huge amount of light onto the metal, but I want to just be able to detect single photons. So how do I do that? Well, I have a photon hit a cathode. A cathode, I mean, you're engineers, so I imagine you know what a cathode is, but just in case. So an electrode is a conductor that interacts with something non-metal. A cathode is an electrode that gives electrons. And then a photocathode is one that is a cathode that produces the electrons through optical stimulation. So that's a photocathode. So the photon hits the photocathode and releases an electron. But detecting a single electron is not so easy. So what we do then is accelerate that electron to another cathode, and that interaction is going to result in more electrons produced. And you sort of get this effect where, oh, sorry, not another cathode. It's going to hit another diode. Excuse me. That's a mistake there. That cathode should be diode. And so, but the idea is the same. You get the one electron comes out, hits this, 2 electrons comes out, hits this one, 10 come out, hits that, 100 come out, et cetera, et cetera, et cetera. Eventually, you have enough electrons that you get a detectable electrical signal. There's other ways to do it. Those of you somewhat familiar with this field might be thinking of avalanche photodiodes or superconducting photon detectors, which are pretty good. My one sort of beef with them is that you need superconducting material, and then you have to cool the thing. And LOQC, one of the advantages is you don't need cooling. So I feel like using superconducting photon detectors is giving up one of the biggest strengths of LOQC. LOQC, yeah. But anyways, so this is the general idea. There's creative ways in which you can convert a single photon into a significant number of electrons. So what do we have next? Qubit control. Okay, so we talked about the beginning and the end of the story. How to produce the electrons and encode produce the photons and encode the qubits in the photons, and the end of the story, how to measure them. What do we do in between? Well, we need single qubit gates and 2 qubit gates. The single qubit gates are done with linear optical elements. There are many different linear optical elements. Here are some. We have a polarizer, so that takes light that's unpolarized and just picks off one element of its polarization. So on this side of the polarizer, we have light with a horizontal and vertical component, goes through, only the vertical survives. I mean, these are all related to phase, to polarization here. We have wave plates, which adjust the polarization of the light. We have polarizing beam splitters, which allow a certain polarization through and reflect the other. These are just some examples of linear optical elements. What they have in common is that the output is a linear combination of the inputs. So you can map this operation with a quantum gate. And so we need at least 2 different types of gates. And here I'm going to be, we're using LOQC, and we're looking at the dual rail encoding. So we want a Z gate. So what we want to do is we want to be able to shift the phase of our qubit. So we're in the 0, 1 state. We want to be able to take that to a state where, so we're adjusting the phase, 0 stays 0, but then 1 changes to 1 with some phase in it. So we have our 2 photons moving through the dual rail encoding, and we want the phase of this one to fall behind the phase of that one. What do we do? Well, we can put a material on the one rail with a different index of refraction. And when it's on that rail, it's going to, you've seen diagrams before of like light sort of oscillating, it goes into some other material and its phase changes. And when it comes out, its phases now can be behind the other one. So we lay out our circuit, and whenever we want to add a Z gate, we can put a little material with a different index of refraction. So with our Y gate, I mean, we could have done Y or X gate, but here it's a Y gate. Sort of like how the math works out is that it also adds something more than just it's more than just an X gate. But we can imagine that if we want to do a bit flip, let's say, so that would be an X gate, we would need the 2 rails to come together because we want the photons to switch from being here to being over here. With a Y gate, we do that with a beam splitter. So the 2 rails come in, they meet as we expect they would need to, and they go through a beam splitter and then come back out into their 2 rails. And by going through the effect of the beam splitter on those 2 modes, we can see that it has the same effect as a Y gate. If you're interested in doing some of these math problems, I've removed pretty much all of the calculations to be able to go over all the concepts. Because as far as I understand, you're not being like tested or quizzed on anything that I'm teaching in quantum computing. So I want you to be able to have an understanding of how these things work, sort of like a practical understanding of that. But if you're interested in doing some math problems to get like your fingers dirty with these, please let me know. There's a great, I mean, there's some texts out there that have questions, and there's examples you can do that I think are pretty interesting. But I'm pretty biased because I work in quantum computing, so of course I think it's interesting. Okay, so that was the 1 qubit gates, but that wasn't the roadblock to optical quantum computing. The roadblock was the 2 qubit gates. So this is the crux of LOQC. This is what made it such a big deal. And the way you do your 2 qubit gate is in 3 steps. First, we do a probabilistic control Z gate. So remember, there's the controlled NOT gate you're familiar with. If the 1 qubit's in the state 1, it flips the other one. A probabilistic Z gate, or sorry, a control Z gate is if the 1 qubit's in the state 1, it applies a Z gate to the other. So there's a way you can create using single photon sources, linear optical elements, and single photon detectors. You can do a controlled Z gate. Actually, I guess you don't need the photon sources. Well, yeah, you do. Okay. All the pieces together, you can make a controlled Z gate. The limitation is that it's probabilistic. It only happens 1 out of 16 times. Now, what's nice is you can use the detectors to know when it happened. But the downside is, say I'm doing an algorithm. I've been running this algorithm. I have a really good quantum computer. I can do quantum computations that take many minutes to do. I get to the end of my computation, and my control Z gate doesn't work. Well, I lost everything. I have to start all over again. So even though it works 1/16 of the time, that's not good enough for scalable quantum computing. We can use, however, a phenomenon known as quantum teleportation to improve this probability. I'm going to speak very briefly about what quantum teleportation is, but I'll explain enough of it to understand how this works. And then ultimately, you can use the process of error correction, which I've sort of alluded to or mentioned before, to reduce the number of resources needed. So you build your probabilistic control Z gate, you improve the probability with quantum teleportation. However, by improving this probability, you're going to add a ton of resources. And then what you can do to reduce the number of resources is take advantage of error correction. I could spend a decent amount of time talking about all of these, but I'm going to focus just on the second step because I think it's probably the only one you can really appreciate without needing to do the math behind it. So I have 3 figures. might look somewhat intimidating, but we're just going to do them one at a time, and it's really not so bad. So let's go over to figure A, or part A here. What I have here is my controlled Z gate. So this box in red, this entire box is everything that happens in step one. So this is my probabilistic controlled Z gate. I have one qubit over here and another qubit over here, psi 1 and psi 2. I want psi 1 and psi 2 to undergo this control Z gate. Right now, A is an incredibly convoluted way to go about it. So why is that? What I have here is an entangled pair of qubits. That's this B00Q. It's a pair of qubits that are entangled. What I use them for is quantum teleportation. What quantum teleportation is, for those of you who haven't seen it, it's you can use an entangled pair of qubits as a resource to take the quantum information from a qubit at one location and transmit it somewhere else. So that's what this whole blue thing here is, this blue box in the XZ. All of this you can think of as the quantum teleporter. So the qubit enters here and it pops out over here, is how you can think about it. The resource we need to teleport it from here to here is this entangled pair. So what is this circuit? I have my one qubit coming along, teleporting over here, my other qubit coming along, teleporting over here, and then they go through the controlled Z gate. Right now, this whole teleporting things over just seems, it's just useless. It's a convoluted way to do it, but it's there for a reason. What I'll do now is take this exact same circuit. So qubit 1 and 2 being teleported from here and here to here and here, and then going through the control Z gate. Exact same circuit, but I'm going to put another controlled Z gate here and another controlled Z gate here. This gate is unitary, so the effect of two of them after one another is nothing. If you notice, this controlled Z gate is now somewhere in this green zone. I'm using this green zone to depict things that could happen before the algorithm. So in theory, I could sort of slide this controlled Z, I could slide this whole box way off to the page. So that way I could prepare this entangled pair before the algorithm starts. So this whole area here, the green region, the takeaway is that this is sort of your offline area. You can do all the work here before you start your algorithm. So now I have a controlled Z gate here being done offline, and I have another controlled Z gate, the rest of the teleportation, and another controlled Z gate. What you can show is that this whole series of gates here is equivalent to this series of gates. Why that's useful is we've now taken our probabilistic control Z gate and we're doing it entirely offline. So you can think of it as, okay, we don't want to do our control Z gate at the very end of the experiment, because if it goes wrong, it screws everything up. So let's do it at the very beginning. And if it messes it up, no problem, we'll just start it again. So that's not a perfect description because, well, for one, it's not like we remove all the probability. The teleportation in this case still happens probabilistically, but it happens probabilistically with a scale that we can improve with more resources. So this is sort of the an overview of, I think, the ingenious that went behind the LOQC. And there's a nice actually review paper on LOQC if you're interested on it. And it was written by, okay, if you're interested, email me. I can send you the authors. But if you type in LOQC review paper, it should come up. I know Raymond Laflamme is one of the authors, but the first author escapes me right now. Okay, so we actually covered everything for LOQC, and that might surprise you because we weren't always explicitly talking about DiVincenzo criteria. But as we go through the criteria, you'll see we actually covered all our bases. So, scalable, well-characterized qubit, single photon sources, we encode them in dual rail encoding, we get our qubit. Scalability, well, we multiple photons. We just generate, put our single photon sources next to one another, line them up. Initialize, well, I mean, there wasn't a lot to that. It just, we produce our single photon sources and we choose which rail we put them in. So we've initialized to the 0 state by putting them in the right rail that it's the 0 state. Gates, we saw that the single qubit gates happen with phase shifts and beam splitters. Our 2-qubit gate is a probabilistic control Z gate that we shift to put the probability at the beginning. Plus, we then do other things, sort of that part of it I didn't go into, but other things to deal with potential errors that could come up later on. Our measurement, we talked about photon detectors. We put them at the end of the rails, and we see which rail the photon is in. And then decoherence, we talked about this a little bit at the very beginning, but essentially the decoherence time with photons is incredibly large. Like losing single photons is somewhat of an issue, but the decoherence time is incredibly long. 1-qubit gates are very fast. It's the time it needs for the photon to move through the optical element. Photons move at the speed of light. And 2-qubit gates are also very fast, but they depend on the measurement and feedback times. So that's my recap of LOQC, linear optics, quantum computing. The next video, we're going to look at quantum computing with atoms, specifically ions that have been trapped. And we're going to look at how well we can do if we create our own atoms or create our own ions artificially using superconducting materials. So hopefully I have you currently convinced that NMR and optics are great ways to go about it. And hopefully I'll convince you of trapped ions and superconducting qubits having different strengths and drawbacks. So I'll see you in the next video.